Well, so a couple of weeks or I think longer ago, a student asked me a question, and the question was very difficult to answer, if answerable at all. I came to realize later that it was the question that was wrong. That was why the answer wasn't available. So, in a kind of mood swings that we all human beings do have at times, I dismissed him. And later I thought that education is not treated that way. Knowledge, when given to you, you have to use whatever means possible to propagate it, especially to someone who asked. So the person asked me who founded quantum mechanics. In the first place, I will express my philosophy of science, that I do not believe in Solomon Kuhn's idea of paradigm shift, which depicts revolutions in science like leaving one room and occupying another new room. No, it is a continuity. This concept, the concept of an atom, has been discussed since the time of Greek philosophers. There were the atomists, and there were those who thought matter was not made of building blocks, of other building blocks. So today we have come to realize that, of course, matter is made up of building blocks, molecules, atoms, some atomic particles, and so on. So I would say the first person to talk about atoms in modern science was the one we present mostly to students was John Dalton. However, when you are teaching atomic physics, I am talking about atom now because quantum mechanics arose from the studies of atomic structure, but it has now become a tool of science that can be applied in any field of science, especially in interaction of matter and energy, or matter and radiation. There are things we do. We teach one atomic model after another. We teach this one today, discredit it the next lesson. Then we say the one we present here is the most is more accurate. Then tomorrow we will discuss. We will discard that one too, and go for another one and say this is the new model. It's like we are telling them, we are learning at the same time that knowledge cannot be exhausted, because when as far back as the early 20th century, people thought there were only three fundamental particles: neutron, proton, and electrons. Then it came to knowledge so advanced that we realized that there is a stream of other particles that are not known. They come from cosmic rays. Some of them are produced in large hadron colliders, where ions or charged particles are accelerated and smashed into one another, into each other, and something else come out. We also realize that decay of a particle is an indicator that the particle is not fundamental. The neutron, for example, does decay, so it is not a fundamental particle. There is quark theory that the nucleons, that is the constituents of the nucleus, neutron and protons, are made up of quarks. Then we are keeping that aside because it has little to do with our question. We will only focus on individual scientists who contributed to quantum mechanics, and a little bit of what they have contributed is enough, because the question was, who invented quantum mechanics? The proper question should have been, how did quantum mechanics evolve? Who were the players? Who were the leading scientists in the invention of quantum mechanics? What each of them has contributed. Dalton's atomic theory gave us two postulates that could not stand the test of time. One is that atoms of the same element are the same everywhere. This is not true. And it doesn't mean that Dalton was wrong. Dalton was working within his own outreach. There were more primitive views. So we realized that no, there are what we call isotopes. For instance, a hydrogen atom, a normal stable hydrogen atom, has one proton and one electron. Then there is heavy hydrogen, deuteron. We call it deuteron because it has one proton, one neutron, and one electron. So the charges on the proton and electron determine the chemical properties of that element. So it is still hydrogen, but it has one more proton and it has one more neutron. And there is another isotope of hydrogen that has two more protons. That means there are three particles in the center with only one electron orbiting, and in the center there is also a unit charge carried by the proton. So we dismissed that. Another one that couldn't stand was that atom was indivisible, indestructible particle of matter. No, we have realized, we have come to learn, especially with the discovery of how to manipulate electricity, especially in vacuum tubes, that the atom is not a fundamental particle. Who did this? There is a British scientist known as Sir J.J. Thomson. He was experimenting with discharge tube. So he got an element heated. The heat emits electrons. That is what we call thermal emission of electrons. And he detected those electrons, and by manipulating the electric and magnetic field on their way to the screen, J.J. Thomson was able to measure the mass, charge mass ratio of the electron. This told him that it is not a complete atom that departed the heated filament, because it is a charged particle being manipulated by electric and magnetic fields. So this is the contribution of Sir J.J. Thomson. Again, Sir J.J. Thomson, after discovering this, Millikan, an American scientist, Robert Millikan, conducted an experiment to weigh the electron. So having got the mass ratio of the electron, charge mass ratio of the electron, and the mass of the electron, we came to know the electron better. Okay, Millikan discovered the mass, so we got the charge on the electron to be 1.6 times 10 raised to the power of minus 19 coulombs. So J.J. Thomson decided to build his own model of the atom. What did he say? We call his own model the plum pudding. He thought that the atom is like a positive field in which the electrons are strategically placed such that they do not interfere with the positive field in which they are embedded. The best way to describe this is the word watermelon. The watermelon, let's assume the tissue is the field, is the positive field, and the, what do they call it? The electrons are like the seeds embedded in that. So that was not a primitive model as far as his time was concerned. That was how much he could reach. So we teach this and say it is wrong. Tomorrow you will teach another one. Then again, there is one property of quantum mechanics, that is, it deals with very small particles. Even large particles obey quantum mechanics, but the frequency is so high, or let's say the wavelength is so negligible that it cannot be treated quantum mechanically. Now, this probability into analysis of systems started with Ludwig Boltzmann. Ludwig Boltzmann arrived at an entropy equation which characterized the macroscopic property of a system, which showed that the macroscopic properties of a system depend on the microstate of the constraint particles of the system. Boltzmann was rejected and he felt dejected. He had problem with that, but today his equation being modified by a German scientist, Max Planck, who we are going to meet soon, is still alive. Let us give an example of what Boltzmann was trying to think. Assume a square box. A square box has, I guess, 8 angles, 2 on the top, 2 in the bottom. So let's assume that the 4 in the bottom are lower energy states. 4 on the top are higher energy states. Imagine you have 4 particles. You have 1 particle at each angle. So the probability of getting at that particle is so easy that it's not much as difficult as if you were looking for the position of the same particle in a hexagon which contains 4 particles, because the particle has the right, like a kind of consciousness, to choose where it would the energy state it would occupy. So your probability increases. The more you increase the energy levels, the more entropic your system grows. So the larger a system grows, the more probabilistic it is to locate a particle within that system. So entropy is always simply defined as disorder. Entropy is not actually disorder. It's not actually an absence of energy, but difficulty in accessing that energy to be used in doing work. For instance, if you have 10 students in a class, I think communicating with them would be simpler than if you have 300 students in a class. There will be chaos, there will be noise. That's a larger system. So the bigger a system grows, the more chaotic it becomes. And that depends on the distribution of microparticles. So this is the beginning of statistical thermodynamics or statistical mechanics, where the distribution of microparticles in the system determines the macro state of the system, such as is determined by macro properties of the system, like volume, and it determines pressure, temperature, and what you have. Because most of quantum mechanics evolved in the study of atom and atomic emission and absorption. We will focus on the atom, and with the nuclear field, the positive field in the nucleus as our potential, and the electron as a particle interacting with that potential field. So after J.J. Thomson, then the discovery of the nucleus came, because J.J. Thomson had no idea of nucleus. So what happened was that radioactivity was discovered, and some elements were known to emit what we call alpha particles. These alpha particles are nothing but 2 protons and 2 neutrons. That is completely ionized helium atom or a helium nucleus. So it carries 2 units of fundamental charges. What Sir Ernest Rutherford and his students did was they fired a thin gold foil with alpha particles. What happened? Some of the alpha particles passed straight, some were reflected at different angles, and some were reflected straight backward. So this told Rutherford that there are spaces between the positive charges and the negative charges in a material. So he came up with a model of the atom, which is a little bit better, but not good enough to describe the actual nature of an atom. So he proposed what we call the planetary model. If you take the hydrogen atom, for instance, much of the mass, according to Rutherford, is concentrated at the center of the atom, while the electrons orbit in circular paths around the nucleus. Much of the weight of the atom is concentrated in the nucleus. We call this planetary model because it was seen how, like the electron is orbiting the nucleus just the way planets orbit the sun. Well, a controversy arose that if a particle is orbiting a central field, it will continue to lose energy and spiral. It will spiral into the nucleus and collapse. It will be emitting radiation. That means it will be losing energy in a continuous manner as the radius get smaller until it falls into the nucleus and collapses. That does not happen. Hydrogen atom is one of the most stable systems in the universe. So where is the magic? This is how the problem started. Then, before we go to Bohr, Max Planck was worried about black body radiation. When we say black body, we mean an ideal absorber of radiation that absorbs all frequencies from radio frequency to gamma frequency, and it can emit whatever it absorbs. So that is a perfect black body. There is a problem associated with that concept of black body radiation, which we will discuss in greater details when we come to talk about quantum mechanics. But let us see what Planck said here. Planck said that the radiation arises from oscillators. These oscillators may be molecules, maybe atoms, maybe electrons, but they must be oscillating along a mean position, but not classically. They jump. When an electron absorbs in every system, whether an atom or an iron rod or whatever, is a system that contains energy levels. So there are energies that the electron cannot assume, or the oscillator, according to Planck, cannot assume. So it can only jump from one allowable state to another allowable state. So when it jumps from a low level state to a higher level state, it must have done that after absorbing a radiation, a packet of energy that is equivalent to the energy difference between the two levels. And at that excited level, if it would go back to the lower energy level, it will give out exactly that amount of energy measured in frequency. So Max Planck invented a radiation formula known as a quantum radiation formula. It is given by energy is equal to frequency times the Planck's constant. The Planck's constant is, energy is equal to frequency times the Planck's constant. The Planck's constant has a value of 6.62 times 10 raised to the power of minus 34 multiplied by the frequency of the photon of light. We will come to talk about what photon is as we progress. Now we are just talking about contributors to quantum mechanics and what they have contributed. Then came Albert Einstein. There was this notion of photoelectricity, that if you shine a beam of light on a metal, the metal may emit electrons. Then, following Planck's Einstein showed that, okay, it is not any energy, because classically high intensity radiation, that is higher intensity radiation, will liberate more electrons. Yes, it will, but higher intensity radiation that is not enough to remove the electron from the surface of the metal will not remove it, no matter how much we increase the intensity. So he proposed something like the binding energy, the energy binding the electron to the metal surface as work function of the metal. So the incoming photon or packet of energy must be as much as the energy binding the electron to the surface of the metal before it can liberate it from the surface of the metal. And if the if the packet of energy that comes in is far bigger than the work function of the metal, that means the energy of the metal, the energy binding the electron to the metal, then what will happen is that the electron will be emitted and the remnant energy, the excess energy of the radiation, will be converted to the kinetic energy of the electron. So it will be shot away from the metal with high speed. We have many names here to talk about, like Ernest Rutherford model of the atom, the Broglie wavelength or the Broglie wave, Schrödinger equation, Heisenberg's uncertainty principle, and the contributions by Paul and Marie Dirac. So we will continue the next video. Meet you that time. But please do subscribe and press the notification button so that you will get our talks or lectures, if we can call them that, anytime we upload. Thank you.